Let's apply what we learned in the last problem to make a prediction here. We have the same spring from spring example 1, and where we determined the spring constant was 300 newtons per meter. And now I've attached a cart to that spring, and I'm going to pull back and let go, and we want to predict the motion of the cart. The mass of the cart is 2 kilograms, and we're assuming a frictionless surface, so we're going to neglect friction. And so we pull it back just like we did before, all the way to 6 centimeters or 0.06 meters. And we're going to let go, and let's predict how fast it's going when it's back here at 2 centimeters. And so we know it started here at 0. That's where the spring is in its relaxed position. And so the spring is still stretched some at this point. We want to determine the speed of the cart. And to do this, we use conservation of energy. The initial energy equals the final energy. And the initial situation is shown up here, and the final is shown over here. The final means the point we're interested in. It could be somewhere else. Maybe I want to know how fast it's going at x equals 0 or x equals 3, just wherever I pick. And drawing a picture is very helpful for doing this energy analysis. And so I look up here at the initial situation, and I'm releasing it from rest, and so there's no kinetic, and there's no change in height, so no gravitational potentials involved. All I have is elastic potential energy. And elastic potential energy is U sub E, and the I indicates it's the initial. And when it reaches x equal 2, the spring is still stretched some, so we have some elastic potential energy, and the cart is going to be moving, and so we have kinetic energy. And so that's our basic idea for this problem. Then we know from the last time that elastic potential energy is 1/2 kx squared. It's the area under a force distance graph. And so quick little derivation there. If I stretch at some distance x, I know the force at that point is kx, and the area is the work I put into the spring, which is the elastic potential energy, and that is 1/2 the base times the height, or 1/2 kx squared. And so that's where that comes from. It's important to know that, because remember what Feynman said, what I cannot create, I do not understand. And so we have the final elastic potential energy at x equal 2, and then the kinetic energy it has. So we need to solve this for velocity. And so a little bit of rearranging, the 1/2s go, and I subtracted kx final squared from both sides, and now I can divide by the mass and then take the square root of both sides, and so that would be the speed at x equal 2. And we put in our numbers, make sure we convert to meters. So I have 300 newtons per meter, 0.06 squared minus 0.02 squared over 2, 0.7 meters per second. If you want to see if you understand how to do this, well, let's just kind of change this around. Same mass, same spring constant. What if I gave this thing a shove in the other direction so that it's going 1.2 meters per second when the cart's here at x equal 2? How far out will it get? Since it's now going faster than 0.7, I would guess it's going to go past here. And so why don't you pause the video and see if you can figure out how far it's going to get. And here's the answer. Hopefully you figured out it is 0.1 meters. So if you weren't able to do that, give it another try.